Well, good morning. We're going to continue on in our discussion of the forensics of environmental science, technology, and law. You'll recall we've been talking about my work in Nogales, where I monitored the amount of particulate matter coming across the border from Nogales, Sonora to Nogales, Arizona, where I went up to the top of the post office and collected volumes of air, collected samples of particulate matter on filter paper, took them to the laboratory, weighed them, and along with the Arizona Department of Environmental Quality, ADEQ, and University Medical Center, Dr. Gerard is the director of Public Health and Management at UMC. And we correlated the amount of particulate matter with the amount of asthma in Nogales Unified School District schools, elementary, middle, and high school. That work was done 1996, and it was published 2 years later. That was an inductive piece of work. Okay? Inductive starts below and reasons up. So for the next 10 minutes or so, we're going to switch now and we're going to go to deductive reasoning, which is reasoning from top down. Okay? You need both inductive reasoning and deductive reasoning to solve environmental problems. My work at the university, which I'll be explaining here briefly in a few minutes. No problems. Includes both inductive and deductive reasoning. The deductive part is going to be explained on this diagram, and the inductive part is going to be explained on this diagram. This article here, air pollution and cardiovascular disease. There is a connection between heart disease and air pollution. Cardiovascular illnesses, hypertension, high blood pressure, cognitive skills can be affected by pollution, skin diseases. We're going to get into that inductive work in a few minutes. Okay. In this diagram here, I got to get on camera maybe. Hello. In this diagram here, I have a conceptual deductive reasoning. And on the x-axis, I've put 0 to 100% pollution. And I've graphed, conceptually now, this data has not been collected, the cost of health care to treat, the cost of treating cardiovascular illness, for example. As you increase the amount of pollution, the incidence of health problems increases, and thereby the cost. You reach a point in the curve, which is called the knee of the curve, yes?
What does 100% pollution mean?
Very contaminated. It's like one of the major cities in China. You can't see your hand in front of your face. So you reach a point in the knee of the curve in this exponential relationship where any small increase in pollution results in a huge increase in cost. So that's the cost of healthcare. Likewise, we can graph the cost to remove the pollution. At 100% pollution, there's no cost. So you're happy with not being able to see the hand in front of your face. As we reduce pollution by putting in technology, sure enough, the costs make sense, right? If you're going to put in technology to remove pollution, the costs are going to increase, and likewise, you're going to reach a knee in the curve, whereas last little bit of removal of the heavy metals or sulfurous acid or particulate matter results in a huge increase to remove that pollution, and that's reflected in the green line here. So what do we have when those two relationships intersect? That's the optimum economic cost. right there. We don't know where that is as a society. It's amazing to me that we've had the Federal Pollution Control Act in effect for 67 years, and we still don't know where this point is. As a matter of fact, 2 years ago, the United States Supreme Court, in its decision in Michigan versus EPA, Environmental Protection Agency, concluded or held that the EPA must consider costs. So the EPA now is frantically running around trying to generate this data. Well, this is very complicated, as you might imagine. There's all kinds of illnesses. There's all kinds of ecosystems. I mean, the optimum for this in Wyoming is going to be quite different in Michigan, where they have a lot of coal-fired energy plants. So each ecosystem is going to have its own characteristic economic optimum as well. This is a lifetime project. I will be dead before we know the answer to this question. But I did present this. Oh, before I go on there. So over here is our current president, and he's in the process of deregulating. He wants to move to more pollution. Our former president, he was in the process of regulating, and he wants to move to less pollution. So we have a political tension from two extremes. Trump, with his unreasonable commercialism, to him the bottom line of profit is most important, whereas Obama is unreasonable environmentalism. He wants to eliminate all pollution. Well, that too, based on this graph, is unreasonable. So there's an optimum that needs to be found. And until we find that optimum, the Republicans and the Democrats are going to continue to fight. The environmentalists and the commercialists are going to continue to fight. And it's a fruitless argument because nobody knows where this is. I presented this diagram to Dr. Gerard, the head of, or the director of public health and management at UMC. I asked him, where do you think we are on this curve? Well, he said, we're very contaminated. Then I asked the same question to the current director of the EPA, a person that was the former Attorney General of Texas, I believe. I asked him, he says, well, we need to have more pollution. We need to deregulate. So even if you ask an individual person, you're going to get a fight. So how do we, well, the question, where do you think we are today? Anybody have an answer to that question? Where do you think we are in this paradigm? Yes?
I feel like it really just depends on like county, not even like the entire United States, because there's definitely areas of the United States that are close to 100%, and there's areas that are close to zero.
Okay, that's correct. That's very perceptive. Thank you. So how are we going to get this data for each particular ecosystem? Well, how many have had calculus? Very important, because calculus is going to give us the answer. If you make a graph, again, this was just conceptual, two-dimensional, but the calculus is three-dimensional. You make a graph of the concentration of a particular pollutant, whether it's lead, arsenic, mercury, copper, sulfuric acid, or even particulate matter. You have on the x-axis concentration. On the y-axis will be the cost resulting from those pollutants, and then on the z is the time of exposure, three-dimensional. So we have two independent variables and one dependent variable, and that can only be answered by calculus. It's not a single two-dimensional line. It's actually a contour. Actually a contour that only calculus can determine. That there is this side of the equation. And similarly, the left side of the equation has to be graphed where concentration, but on the z-axis it'll be amount of production of the pollutant. instead of time to exposure, and then the cost to remove. So where those two contours intersect, that'll be the optimal cost for the particular ecosystem. Any questions? Any additional questions? Yes, sir.
How long do you think until we find it optimal?
It's, well, for any particular ecosystem, maybe 5 years from now, 7 years from now, huge opportunity for the forensic scientist. Huge opportunity to get a complete optimum for a mixture, like say in Michigan, where the coal-fired energy plants are introducing lead and arsenic and mercury and copper and sulfurous acid to the environment. 10 years maybe? So, good question, thank you. So, at that, I'll conclude the video. Thank you for your attention. Adelante.